Good morning, everyone. Are you able to hear me?
Yes.
All right, thank you. Okay, so let's start our lecture today. But before that, just want to go through what we have, what I have shown you in the previous video, right? So this is a very important one, okay, which is about the line integrals of a vector field. Okay, so this is the class that I talked about in the previous video during the Christmas holiday. Okay. So this is about the line integrals of a vector field. All right. So how to know whether this is a line integrals of vector field? You can see that this is the formulas for the line integrals of vector field. Okay. You will see the f is a vector. Okay. Dot product with the dr. Okay. So here there are some things that you need to understand about the dr over here, which is this thing. Okay, so this is always valid for all the line integrals. Okay, the r is always equals to xi plus yj plus zk. Okay, so when you perform the dr, you will get this thing. Okay, you will get this thing over here. Okay, so you can change it, you can differentiate it with respect to the t or x or y. Okay, it depends on the equations or relationship between the line. Okay, so when you perform a dot product, in the end, you will find that it is like line integrals. Okay, line integrals of a scalar field. Okay, so you just continue to solve these line integrals. Okay, so I give you an example over here. Okay, how you actually do the differentiation with respect to the t in order to get the dr dt, and then you replace it here. Okay, and then you get the final answer. Okay, so these line integrals of vector field also defined as the work done. Okay, as a work done by the force. Okay, to move a particle along the curve C. So in fact, there are a few ways for us to find the work done. One is to solve the line integral just like this thing. Okay, you solve this thing. The other is you try to prove that the force is conservative, and then you will find the potential functions. Okay, and from the potential function, you'll find out what is the work done. So in order to prove that the force, the F is conservative, okay, so we will try to do find the answer when we are going when we perform the line integrals of vector field by using different path. Okay, for example, like this example, I use the straight line. Okay, so this is the straight line. Okay, the path is a straight line, and then we do all the line integrals of vector field, blah blah blah. We get one answer over here, and then this is a curve. This is a quadratic curve. Okay, then we do it as usual also, and then we get the other answer. Okay, so if you find that all the path will give you the same answer, okay, same answer, that means that, okay, so this line integral is independent of the path. Okay, so this is independent of the path. When it is independent of the path, then it is conservative. Okay, when it is conservative, it means that there will be a scalar function over here. Okay, so this is a scalar functions. Okay, so this scalar function, when you perform the gradient of it, you will get the f. You will get the f over here. Okay, you will get the f over here. Okay, so another properties of the force that is conservative is, okay, when you perform the curl of the vector f, you will get answer equals to 0. Okay, so this example 4.25 is you trying to prove that the f is conservative, and then you find the potential functions. Okay, find the potential function, and I explain to you. I explain to you how to actually combine the potential function, okay, from both integration with respect to dx and integration with respect to dy. So if you have similar term, okay, when you perform the differentiations, okay, and when you perform the integration, you should just add them once, okay, once time only, okay, you cannot add them to become 2xy. Okay, this one will give you the wrong answer. And for the work done, you just take the potential function that you have find it, okay, and mark the starting point, okay, the starting point and also the ending point. Okay, replace the value of x and y into the potential function, you can get the work done. Okay, any questions you want to ask about these line integrals of vector field? Is there any questions?
No.
No, huh? All right. Okay, so we go back to our lecture today. Okay, so today we are going to the surface integrals of vector field. Okay, you can look at page 173. So for this surface integrals of vector field, sometimes we call it as a flux integral. Flux integral. We are trying to find the flux that coming out from the surface. So in order for you to imagine better about what is a flux, okay, just imagine like this is a balloon, like I explained in the class, a balloon, and the balloon is filled up with water, so much water inside. Okay, so if you make tiny hole on the surface of all these balloons, the water will burst out in these directions. Okay, so this one we call it as a water flux. Water flux. So by conducting the surface integrals of vector field, we are able to find out what is the flux. Okay, so this is the flux. Okay, coming out from the surface. Okay, so for the surface integrals of vector field, okay, the formula will be double integral, and this sigma, okay, represent the surface. Sigma represent the surface. Okay, so this represent the surface. Okay, that you want to know the flux coming out. Okay, then you will have a F. This is like the vector. Okay, the force. Okay, and dot product with the n. Okay, so this n is the unit vector normal. Okay, label it as the unit normal vector. Sorry, unit normal vector. Okay, unit normal vector, and last one is the ds. Okay, so this is the formula of the surface integrals of vector field. Okay, so this term, okay, this f usually will be given by the questions. Will be given by the questions. Okay, you need to find out, okay, this n, okay, and also the interval, okay, the interval of your double integral. Okay, so these things are the things that you need to find out. Okay, you need to find it. Okay, fine. Okay, you need to find. Okay, so now let's look at what is this unique normal vector. Okay, what is this? Okay, so you have two formula for this unique normal vector. Okay, it depends on whether your flux is oriented upward or oriented downward. Okay, upward means what? Upward means for example, you have a plane. Okay, you have a plane. Okay, this is one of the surface lah. Okay, upward means that the flux is coming up in this way. Okay, so this is the flux. Okay, flux oriented upward. Okay, coming out from the surface. Coming out from the surface. Then we call it as the upward. Okay, if the flux is in opposite direction, means that it's downward. Okay, we said that this is the flux oriented in downward directions. Downward directions. Okay, so this happens, okay, for the plane, okay, for a surface which exists in the form of plane. Imagine if you have a sphere. Okay, if you have a sphere. Okay, upward flux meaning that the flux is in the outward direction. Okay, moving away from the surface. Okay, see, I use the black color arrow to represent that this is the flux outward. Okay, if the flux is going into the surface of a solid, then we say that this is the flux inward. Okay, so the flux downward and inward will have the same formula. Okay, and for the flux outward, this one, oops, upward, sorry, upward. Okay, this one and this one will have the same formula. Okay, so what are the formula? So for the flux downward or inward, you can refer to your module. Okay, the unit normal vector is equals to this one, del z over del x. Okay, and you have the I, okay, plus del z del y, you have the j and minus k, okay, minus k, and divide with this. Okay, so this one is the del z del x square plus del z del y square plus 1. Okay, this happens when the flux is downward and inward. On the other hand, okay, if your flux is in the upward and also outward directions, okay, so your n would be, I will write here, unit normal vector will be, this one I write in simple way because I have limited space. Fx, Fx means that the z equation you differentiate with respect to the x. Okay, and okay, use this symbol, comma, fy, okay, and 1. This is a vector because I have limited space, that's why I write in this way. Okay, and here it would be fx square plus fy square plus 1. Okay, so this one will be the formula for the upward, okay, upward flux. So this one will be for the downward or inward. So what is the difference? What is the difference? So you can see over here it is positive. You can see over here it is positive. Positive, positive, and negative. Okay. On the other hand, okay, here is negative, negative, and positive. That's the difference between the unit normal vector for upward and also for downward. Okay, usually the question they will mention whether it is inward or outward. So you will choose, okay, the one that is mentioned by the questions. Okay, and let's look at one example. Okay, one example so you know how to apply it. You know how to apply it. We look at example 4.31. Okay, next page. Page 174. Example 4.31. Okay, so let sigma, okay, this is sigma, okay, sigma, S-I-G-M-A, okay, let sigma be the surface of the plane. Sigma is the surface of the plane. Okay, so this plane has equation z equals to xy. Okay, so the limit for the x and y, okay, is from 0 to 1. This is for the x. And for the y is from 0 to 2. 0 to 2. Now the F, the force, okay, or the field, okay, is equals to S Z. Oh no, I'm gonna write this way. 0 X Z X Y. Okay, so this is given by the questions. Okay. So now this is the vector field that passing this sigma, passing this surface. Assume that the n is the unit normal vector oriented outward. Question said that it is outward. Evaluate. Okay, evaluate what? Evaluate this. Okay. Evaluate these surface integrals of vector field. Okay. They ask you to evaluate this one. Evaluate. So you jot down all the information that is given by the questions. Okay, and try to understand what you need to find. Okay, so we go through the parameter one by one. So for the f, it has been given by the questions. Okay, so we move on to the n. Okay, we move on to the n. Okay, we move on to the n. So n is outward. Means that the flux is going out from the surface. It's going out from the surface. Okay, so which formula we should use? It's outward, 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 out, right? Outward. Okay, the black color one, outward. Okay, so we should use this one. This formula. Okay, so I will write in this way. I will write down the formula first. Okay, so you know what you want to do next. This is the x. I will use this thing. Okay, easier. Right? And 1. Okay, so this meaning this is I component, this is J component. Okay, and this is K component. This is K components. And this thing represent that is a vector. Okay, it's a vector. So divide with the fx square plus fy square plus 1. Okay, so this is the formula. Okay, so we want to find out what is the n. So the first thing that we must know is what is the f, right? What is the f? So the f is the function that represents the surface. F is the function that represents the surface. Okay, where our surface is equals to z equals to z, and z equals to x, y. Okay, this is our surface. Okay. So when we want to perform the fx, it means that we're doing the del z del x. Okay, so this one will give you the answer y. And fy equals to del z del y. And it is equals to x. Why I need to find this one, fx and fy? Because it is required over here. Okay, it's required over here. So when after we done the differentiations, right? Okay, we can write down our n is equals to negative, okay, negative y, negative x, and 1. Okay, and for this thing, I will just remain this thing first, okay, because later I want to explain to you, it will be cancelled out. Okay, it will be cancelled out, so I don't want to replace anything here first. Okay, so this one will be your n, unit normal vector n. Okay, so see, you have complete this one you have complete. Now we move on to the dx. What is dx? So the dx here is equals to fx square plus fy square plus 1 dA. Okay, plus 1 dA. This one, where is it? This one is actually, okay, where this from? Okay, maybe you will ask, where this from? Okay, so this one is from page 169. Okay, surface integral of scalar field. Okay, we didn't cover this one. We didn't cover this one. Okay, so this equation is from this page 169. You can refer it. Okay, you can refer it. So we go back to our ds. So ds is equal to this thing. So you just imagine if I put this dx, okay, here and multiply with the n. You look at the n term here. It is exactly the same as this one, right? They are the same. Okay, they are the same. So you can just cancel it. They are the same. Cancel it. Okay, so now we put all together. We put all together. You know, they are the same and we can cancel it. So f, okay, equals to, I'll put this thing like 0 x z x y. Okay, so this is my f, and I dot product with the unit vector n over here. Okay, so we just copy first. Negative y, negative x, 1. Alright. I think this thing I will just show you first. I'll show you first. Next time I won't show anymore. Okay, just want to let you know that this thing will be cancelled out. Okay, and multiply with the ds. Ds is this one. Okay, and dA. Okay, see this thing? Okay, so this is the f dot with the n, and ds is here. Okay, so the whole thing is ds. Okay, and this is your n, and this is your f. Clear? Right. Okay, next we can simplify it by cancel this term. Cancel these terms and continue with the double integration solving. Okay, so this one you can do the dot product. Okay, so for the dot product you will get a scalar. Okay, so you for the first term 0 multiply negative y, you get 0. Okay, and minus x squared z and plus the xy. Right? Okay, and here is the dA. Okay, so remember this dA is for you to define a dx dy or dy dx. Okay, so this question already give us what is the range for the dx dy. Okay, so we just replace it. Okay, we can just replace it. Okay, so I put dx dy. So for the x, it is from 0 to 1. 0 to 1. And for the y is from 0 to 2. This one is given by the questions. Given by the questions. Okay, next one. We continue to solve this thing. Okay, so we have to solve it manually because it has more than one variable. More than one variable. Oh, yeah, before that, you can replace this z. Let's replace this z because the z you can write it as x squared. Z is equal to xy. Okay, so this is the equation for the surface. Okay, z equals to xy. See, z equals to xy. Then plus the xy, dx, dy. So let's solve this thing. You could get negative x cubed y plus xy. So dx, dy. So let's solve this thing. integrate with respect to the x, you get negative x power 4 over 4. So the y, you remain right. And for the second term, x power 2 over 2, y remain. Okay, don't forget about the value. Okay, so now you replace the x with 1 and 0. Okay, so negative 1 plus 1. Okay, so for the 0, it will be 0. Okay, so I won't write it out. Now you can continue to integrate with respect to the y. Okay, so for this part, you can do manually or you can use the calculator to get the answer. Okay, you can use calculator to get the answer. So try to get the answer, which is equals to 0.5. Okay, 0.5. So this is how you find out the surface integrals of vector field. Surface integral of vector field. Okay. Everything okay? Are you clear about the steps and procedure? Okay. First one would be you find out the n. Okay. Find out the n, and you identify which equation you want to use. And next one is you identify what is your f. Okay, so the f normally would be the equation of the surface. Okay, so you find the fx, you find the fy, okay, and then you replace it into your equations for the surface integral of vector field. So you have put the f, you put the unit normal vector, okay, and the ds is this one. Okay, ds is always this one. It's always this one. Okay, and then perform the dot product. Okay, perform the dot product and get this thing. And next is to define the interval for the dA. In this case, question gives us the interval for x and y. So we will just use this interval and finally calculate the answer like usual. Okay? Is that okay? We look at one more example. Example 4.32. Okay. Next page, page 175. Example 4.32. Okay, 4.32. So compute the flux of water. Flux of water, something like I explained just now, a balloon filled up with water. Okay, so the water coming out from small tiny hole on the surface. Okay, flux of water through the cone. So now your surface is a cone. Your surface is a cone. So the cone has equation z equals to 4 minus. Okay, so this is the equations of your cone. And this cone lies above the plane z equals to 0. Okay, it's above because the cone can extend downward, okay, to negative infinity. But it just mentioned that, okay, you just cover the part that is above the plane z equals to 0. Okay, and oriented by an upward unit normal vector. Okay, so you jot down unit normal vector is upward. Just jot down the informations. The velocity vector, okay, f. The f is given as 3x I, 3y, j, and 6k. Okay, so this is the velocity vector. Okay, so now you have to find the flux of water. They didn't mention about the surface integral of vector field, but still remember I mentioned that the surface integral of the vector field is also known as the flux integral. You want to find the flux coming up from the surface. Okay, so this also means that we need to find out this. The flux. The flux coming out from the surface is equals to you perform the surface integrals of the vector field. Okay. Right. So this is something that you need to solve. Okay. So let's go through this process one more time. Okay. So F, you know it, N. So the N is upward. Okay. Upward. We have to use these equations. Okay. Okay, so this is the equation that we will use to find the flux. Anyone is not clear about these equations?
Clear, madam.
Clear? Well, very good. Thank you for the response. Okay, now we find what is F. F is the surface. Okay, so here we have a cone surface. The cone has an equation Z equals to 4 minus square root x squared plus y squared. Right, this is our cone equations, our surface. So we need to find out what is the fx, right? So we need to perform del z, del x, and also del z, del y. Okay, we need to find this thing. Okay, so how to find this thing? Okay, so for this one, fx, 4 will become 0. Okay, so this one you just imagine it could be right as power 1 over 2. So that's why when you perform the differentiation, you will get 1 over 2. Okay, you get 1 over 2. Oh yeah, you have a minus. You have a minus. So here you must have a minus. Okay, 1 over 2 x squared plus y squared power negative 1 over 2. And for the x itself, you get 2x. Okay, so you can rewrite it so that it looks better. So you have an x squared plus y squared square root, right? So you have a negative here, and this negative is from here, okay? Now we move on to the del z del y, very similar, okay, very similar. So you will get 1 over 2 x squared plus y squared negative 1 over 2. And the difference here is you need to differentiate with respect to y. That's what you get 2y here. Okay, so the same step, you can write it this way. Right. Now, I have all the fx, fy, right? So this one settle, settle. All right. So now let's put whole thing into this flux. Okay, let's put it here. So the flux coming out from the surface, it will be double integral. And the f here is 3x, right? 3y and 6. This is a vector. Dot product with the unit vector n. unit vector n. So what is the unit vector n? Remember, we have the negative fx. Okay, negative fx is equals to x over square root x squared plus y squared. And you have a negative. And then negative y, fy. Negative, negative y. Okay, comma 1. Okay, 1. Yeah, because here is equals to 1. Okay, so I don't want to write down this part, okay, because it will be cancelled out with the ds term, right? So I straight away write it as the dA. Huh? I cancel it. I cancel it straight away. Okay, next, let's simplify it. 3x, this one will become positive. 3x squared over square root x squared plus y squared. Okay, and plus the second term. Okay, 3y squared over x squared plus y squared. And the third term will be 6. Okay, will be 6 dA. Okay, so when define the dA, okay, just like what we have learned previously, finding the area, finding the volume, okay, we have to look for the projections. Okay, we have to look for the projections. So our structure is the cone. Okay, it's the cone. So question asks us only consider the cone that is above the plane z equals to 0, which is this one. Okay, so this point you can find out as 4. This one you also can find out as 4. How to know this one is 4? You can look at the equations here. This is your equations. Okay, so the maximum value of your z will be 4 because 4 will be minus with something. Okay, minus with something, so the value will be lesser and lesser. 1, ada soalan ke? 1 Basir, do you have any questions? Okay, so we go for the projections. Okay, so projection will be x1 projections, because that is easier for you to define the dA, right? Okay, so you will see a circle with radius of 4. Radius of 4, Okay, so in this case, okay, we will use the dA of cylindrical coordinate system, okay, or polar coordinate system, okay, because the projection show us a circular structure, okay, so it will be easier for us to consider our dA, okay, as r dr d theta, okay, r dr and d theta. Okay, so it is a complete circle. So you will have a theta 0 to 2 pi, and the radius is 0 to 4. Okay, like in the drawing. So before we solve these things, we must convert all the x, okay, and y, okay, so that you won't see them anymore. You just want to see the r and also the theta. Okay, so let's try to simplify it and convert it. So you can combine this one as 3x squared plus y squared. You factor it out and over. Okay, so this thing could be write it as what? R squared, right? Because x squared plus y squared equals to r squared, and plus 6 you can remain it. Okay, and in fact this one you can write it to be r squared. Okay, r squared. So it will be 3r squared over r plus 6. Okay, here you got one more r. Okay, so in fact you can multiply it into the bracket. So I straight away multiply it. So you get this one. Okay, so you can press calculator for the first term because you only has the r component, right? You can press calculator. Let's press calculator. Integrate 3x squared plus 6x. So you get 112. 112 d theta. And later on when you perform the integration d theta, you get 224 pi. Okay, you just multiply it. Okay, multiply it. Okay, so in the module you see that the flux it has unit because it's in the questions. Okay, they mentioned that the density is 1/10 over m cube. Okay, so you write it as m cube over second. Okay, so what does this mean? Okay, so it means that for 1 second there will be 224 pi meter cube of water coming out from the surface of the cone. From the surface of the cone. Right, so this is our second example about the flux integral. Is there everybody okay?
Okay.
All right. Okay, so we move on to the next part. Okay, next section. Okay, page 176. 176. Okay, that is the Gauss theorem or the divergence theorem. Okay. Okay, a new section, or sometimes we call it as a divergence theorem. Okay. So what this theorem used for? Okay, why we want to use this theorem? Okay, so what we have learned previously about the surface integral of vector field is we want to know the flux coming out from the surface. Okay, so usually, in the real application, we will prefer to find out what is the flux coming out from a solid. For example, if you have a cube, if you have a cube, so the cube has 6 surfaces, right? This is a 2. So here you have 3, and then 4, and then side 5, and the bottom you will have 6. 6 surface. Okay, 6 surface. So if you want to know the flux that is coming out from this cube, this solid, means that you have to perform the surface integral for 6 surfaces. Okay, so you have the surface 1. Okay, try to calculate how much flux coming out. Okay, next will be the other surface. Okay, how much flux coming out. Next will be this surface. Okay, you try to calculate how much flux coming out. And another surface at the bottom. Okay, what is the flux coming out, and then what else? Behind. Oh my god. Behind. Right, behind. What is the surface? What is the flux coming out? And in front, you have 6. Okay, you have to calculate these, okay, surface integrals of a vector field or the flux integral for 6 times. Okay, 1, 2, 3, 4, 5, 6. Because this solid has 6 surface. Okay, so this process is very long, right? Many steps because you have 6 surface. Okay, so if we apply the Gauss theorem or the divergence theorem, we could find the flux coming out from this solid with just single step. Okay, that is this. Oops. Okay, so this is the surface integral. Okay, so we could just use this one, triple integral. Okay, divergence of the f and dv. Okay, we could just use this one to find out, okay, the flux that is coming out from the surface. Okay, we look at example, okay, example 4.33, then you will see what is the usage of this divergence theorem or the Gauss theorems. Okay, so given that, okay, sigma are the surface of the cube, okay, surface of the cube, so many surface, which is bounded by, okay, so these are the limit, okay, of the cube, okay, 1, 1. Okay, so this is the dimension. We could say that this is the dimension of your cube. Okay, oriented outward. Okay, oriented outward. Down. Okay, and with the force is equals to x, 2y, 3z. Okay, so verify the Gauss theorem. What is the meaning of verify? Okay, verify, it means that you have to prove that the answer at the left hand side, okay, this is left hand side, is equals to the answer at the right hand side. So this is the meaning of verify. Okay, but here I don't want to do the left hand side. You can look at your modules. Okay, so for 6 surface of this cube, you have to perform the surface integrals of vector field, which is this one, the left hand side, for 6 times. Okay, for 6 times. Okay, so you can look at the steps. Okay, and the total flux that coming out from the solid will be the summations of the flux coming out from each of the surface. You have 6 surface, okay, right? This one you already shown in your module. Okay, so you have to, if you want to find the flux coming out from the surface, you have to plus the flux coming out from the first surface, second surface, third surface, 4, 5, and 6. Wow. So you have to perform the surface integrals for 6 times. Okay. Now let's look at how we can solve this thing using the divergence theorem. So just perform one time calculation. You could get the flux coming out from this cube. Okay. So I'm going to show you about the calculation of the right hand side. Okay. Right hand side. So this is a triple integral, and you have the divergence of the vector f, okay, multiply with the dv. Okay, so the first step that you need to do is, of course, to find out what is the divergence of this vector f. Okay, so this thing we already learned it before that. Okay, I already show you how to find the divergence of vector f. Okay, so the divergence, the del, in fact, it represents this thing. Okay, I plus del y j plus del z k. Okay, so this is your del. Okay, when it dot product with the f, okay, remember your f has a term, right? Your f has the xi, okay, and 2y, right, and 3z. Okay, so when you perform a dot product means that, okay, this term you differentiate with respect to x, you get 1, okay, and the second term you differentiate with respect to y, you get 2, and the third term you differentiate with respect to the z, you get 3. So you get 6 for the divergence of this vector f. So you put the 6 in your formula, okay, and now you need to decide the dv. Okay, dv, v stands for the volume. Okay, so questions already tell us that what is the dimensions of the cube. Okay, so you could use the Cartesian coordinate to represent your dv. Okay, you could use the Cartesian Cartesian coordinate. It means that it is dx, dy, and dz. Okay, so for the interval of the x, look at the module, look at the questions. It's from 1 to 0, 1 to 2, sorry. Okay, for the y is from 0 to 1, and for the z is from -1 to 1. Okay, so I think this triple integral is very simple, right? Very simple. Okay, so you can solve this thing easily. Or you want to press calculator also, no problem. Okay, you can press calculator. So it will be 6. Sorry, dy dz, dy dz. Right. So you left is 6, right? So you integrate 6, 1, 0. You get 6 also, right? So you get tough. Okay. So this answer is the same as the answer, okay, from the left hand side. Yeah, I didn't do the left hand side, but you can refer to the answer in your module. Okay, the left hand side also give you the answer 12. This one also 12. Okay, but which one is simple? Of course, the steps using the divergence theorem is simple. Okay, because too many surfaces for this cube. Okay, so there are too many steps. Okay, so if you use the divergence theorem, it could simplify your calculations. Okay, in the exam, if they ask you to verify or prove, meaning that you have to do both sides, left hand side and right hand side, and you prove that the answer are the same. Okay, remember, if in the final exam they ask you to verify, ask you to prove, you must do both sides. Okay, if you just do one side, you can only get half of the marks. Right, because this is the meaning of verify. You have to verify. Now let's try one example because in our previous example, example 4.32, right? Example 4.32 about the flux of water coming out from the cone. This one, this one. Yes, this thing. Right. Okay. So we already get our answer, right? We get 224 pi. So can we try to verify by using the divergence theorem? And let's try to verify using the divergence theorem. Okay? Right. Okay. example 4.32, page 175. Okay. So same questions, huh? So I just write down the information again. You have a con. Okay, then you have the F. Okay, so we want to find the flux of water coming out from the cone, from the cone. So we want to apply the divergence theorem. This is this dV. Okay, so this is the flux of water. Flux of water, okay, from the cone. Okay, we're going to find out. Okay, so the first step is to find out the divergence of F. The divergence of F. Okay, so let's find out the divergence of F. So it will be del X, del Y, del Z, dot product with the 3X, 3Y, and 6. Okay, I'm doing this part. Okay, I'm doing this part now. Okay, so what's the answer? You will have a 3 plus 3 plus 0. Huh? Am I right? 3 plus 3, 0. Huh? Okay, so you get 6. Right, 6. Huh? Okay, so now we put it here, 6. Can anyone tell me what kind of, which coordinate system is suitable for this cone structure? Can anyone tell me? Because I want to define the dV. Which one? Cartesian, cylindrical, or spherical?
Cylindrical.
Yes, cylindrical. Okay, so the dV for the cylindrical will be dz. dz, r, dr, and d theta. Okay, so which means that I have to find the range for dz, dr, and d theta. Okay, I think dr, d theta no problem for you, right? Because just now we already defined it. Okay, the r is from 0 to 4, theta is from 0 to 2 pi. How about the dz? Okay, so dz, you just imagine this is your cone, right? Let me draw the cone for you. Okay, just sketch it cone. Okay, when you want to define the dz, okay, z, this is the z-axis, you have to always imagine yourself is sitting inside the cone. Okay, so the lower limit for the dz will be at the bottom. At the bottom, it is a flat surface. Flat surface at the position z equals to 0. Okay, z equals to 0. And when you refer up, okay, you didn't see a flat surface, but you see a surface that is actually covered by the equation of the cone. Am I right? Okay, the equation of the cone is 4 minus x squared plus y squared square root. This is what you will see. So these two will be your lower and also the upper limit of your dz. Okay, so I will put here. Okay, upper limit will be 4 minus this one. Okay, just put here first. Okay, since I want to solve using the cylindrical, I don't want to see the xy anymore. So I should rewrite it. So 4 minus r. Okay, it will be 4 minus r. Okay, 4 minus r. This is 0. This is 6. Okay, dz r dr d theta. Okay, so let's do the integrations. So for the first integration, we have to do manually. So the integrate with integration is not differentiation. Integrate with respect to the z, you get 6 4 minus r. Okay, 4 minus r. And now you have this r here. So next is to perform the second integration. So you can expand it into 4r minus 6r squared. Right. Or you want to press calculator directly also, okay? No problem. Okay, so you press calculator. 24r minus 6r squared. 4 and 0. Yeah, you get 24 d theta. And lastly, it will be 128 pi. Is it the same as the answer that we calculate just now? Is it the same?
No.
No. Right, just now the answer is what? 224. Just now the answer is 224 pi. Okay? Now our answer is 128 pi. Why? Why is not the same? Can anyone tell me why it's not the same? Anyone? Do you know why?
I don't know.
Okay, Harry, you don't know. How about the others? Do you know why? Yeah, so this is the yes. Yes, anyone? So this is a divergence theorem, huh? Okay, so the divergence theorem for us to find out the flux coming up from a solid. Okay, so this is a surface integral used to calculate the flux coming up from the surface. This is from the surface. Flux coming out from the surface. This is for the solid, right? If you want to put them in the same, if you want to find out, if you want to verify both of them, you must add all the surface together. Surface 1, surface 2, and blah, 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 and so on. Let's look at our cone just now. Okay, so this is our cone just now. Can you tell me how many surface does this cone has? How many surface? The proper surface this cone?
Dua. Two.
2, right? Okay, the first surface is this one. Yeah, this is the first surface. And the second surface is the one at the bottom. Okay, which we didn't calculate just now. So of course lah, okay. So the answer that we get just now will not be the same as the answer that we calculate using the divergence theorem. Okay, so let's prove it. Let's prove it. How to prove? Here just now we know that it is already 224 pi, right? Now let's find out what is the flux coming out from this second surface. This is the second surface, surface 2. Okay, so look at this surface 2. So we use the same equations, this one, because we want to calculate the flux coming out from the bottom surface. Okay, so F has been given and is not given. So what do we think about the directions of this N? It would be inward or outward. Which one? Can you tell me? Inward.
Outward.
Yes, outward. Why outward? You just imagine water is inside the cone. Okay, so when the water come out from the hole, of course the water will be going outward. Okay, water will be going outward. Okay, so what is the outward equations? The outward equation is, okay, you refer. If you cannot memorize, okay, you can refer first. Negative fx negative fy 1 with this fx fy and 1. Okay, this is your formula. Okay, now we find out what is our f for this surface at the bottom. This is the surface at the bottom. What is the equation to represent this surface? Anyone? What is the equation to represent this surface to? Z equals to? Anyone?
4
Where is the
minus
that one is this surface. 4 minus square root x square plus y square. Okay, represent the slanted surface of the cone. Okay, for the surface 2, okay, the z is equal to 0. Do you agree?
yes.
Yes, doctor.
Right, yeah, wait. Outward, downward. Oh, sorry, this is a downward. This is downward. Sorry, this one is downward. Going downward. I cannot write like this. Upward, downward. Because it's a surface. It's a surface. Okay, so this one should be because it's a surface, because it is a surface. So just now it should be should be asking whether it should be outward or downward. Okay, so the answer is downward. Answer is downward. Okay, so you should choose the other formula, which is this one. Okay, downward. Okay, right. So the equation for the surface 2 is z, and it is equals to 0. Okay, so when the z equals to 0, it means that fx is 0, fy is also 0. Okay, so these two 0. So you just left this negative 1. Okay, negative 1. So this one will give you negative k. Negative k over square root fx or 0. Okay, so this one is all 0. So you will have this equals divide 1. Because 0, 0. Okay, so you see this one is the unit normal vector. So you just imagine this is your cone, right? So the water coming out this way. Okay, coming out. Okay, so this one going down. Okay, going down. Okay, so it is in the negative k directions. Negative k directions. Okay, so after we get this thing, we put it into our equations. Double integral. So the f is equals to what? 3x, 3y, 6. And dot product with this 0, 0, negative 1. 0, 0, negative 1. Or maybe I should write here 0, 0, negative 1. Better. 0, 0, negative 1. It's the same. Okay. And dA. Okay. So this dA, we'll use the polar coordinate. Polar coordinate. Okay. So use r dr d theta. Okay. So let's put the range 0 to 4, 0 to 2 pi. Okay. So you get negative 6. You get negative 6 r dr and d theta. So let's solve for the integration with respect to the dr. So negative 6x 4, 0, you get negative 48 d theta. Okay, and you get negative 96 pi meter cubed per second. Okay, so this is the flux coming from the bottom, coming from second surface, surface 2. Okay, so let's add them together. Just now it's negative 96, 96 pi. So what will be the total? Okay, 224 minus 96. Yeah, you see you get 128 pi. Okay, which is the same as this one. Okay, so let me do this thing. From the surface 1 plus surface 2, okay, it will be 224 pi minus 96 pi. So you get 128 pi. Okay, so this answer will be the same as the answer from divergence theorem. Okay, any questions? Do you understand what I'm doing?
Yes.
Okay, so surface integral of vector field, okay, we just consider the flux from the surface, okay, but for the divergence theorem, it consider the flux from the solid. It don't care how much surface or how many surface you have for the solid, okay, it will just calculate lump sum, okay, at once. All right, okay, so we still have some time. Okay, we move on to the last sections of this chapter, okay, which is the Stokes theorem. Stokes theorems, page 182. Stokes theorem. Stokes theorem. Okay, so this Stokes theorem is a bit similar like the divergence theorem. Okay, divergence theorem is to convert the surface integral into the volume integral. Okay, but for this Stokes theorem, it is converting the line integral to the surface integral. Okay, so line integral, we have learned this thing, right? Line integrals of vector field. If you still remember, this is a symbol. Okay, we can convert it or simplify it, okay, as the divergence, using the divergence theorem to become curl of the vector f, and this is the ds. Okay, this is the ds. Okay, so let's look at one example. Example 4.36. Okay, we'll try to verify. Okay, we'll try to verify. Example 4.36. Okay, page 182. Okay, so sigma be the portion of a paraboloid. Okay, sigma is a surface. So let me draw the paraboloid surface. So this is a paraboloid surface. Okay, so you have the z, you have the y, and you have the x. Okay, so sigma be the portion of paraboloid. Okay, sigma is this surface. Yeah, sigma. Okay, so this surface is z equals to 4 minus x squared minus y squared. Okay, z is greater than 0, and z is greater than 0, oriented outward. Oriented outward. Oh, here I mix one parameter, that is the dot. Dot unit vector number. Okay, so this one is outward. Okay, this one is outward. Where C is the boundary. C. See, remember this one here we have a C. Is a curve. Okay, so C is the boundary of the sigma in the xy plane. Okay, so where is this C? So C is referred to this one. Okay, so this is the C. Okay, verify Stokes theorem if your F is equals to this one. 2z, okay, 3x and 5y. Okay, so the meaning of verify is we have to prove that the left hand side is the same as the right hand side. Okay, clear? Left hand side is same as the right hand side. Yeah. Okay, so we go to the left hand side first, which is this one. Okay, so f has been given. We have no problem on the f. How about the dr? How about dr? Okay, r is equals to, if you still remember, r equals to xi plus yj plus z. Okay. Okay, so the dr, okay, will be this one. Okay, you can use this thing, dx. Okay, plus dy plus dz. Okay, you can just remember these two. Okay, you can remember these two. Okay, so when we perform this line integral, okay, we perform this line integral, you put them together. So the f would be 2z, 3x, 5y, dot product with this one, dx, dy, and dz. Okay, we continue simplify it. So it's 2z dx. Okay, 2z dx plus 3x dy plus 5y dz. Okay, just to perform the dot product. Okay, perform the dot product. Okay, now we look at the position of this C. Okay, we look at this C. This C is in the circular form located at the position z equals to 0. Okay, so when the z equals to 0, dz is also equals to 0. Okay, so we can cancel out a few terms in the integral. We cancel out. So we left this 3x dy. Okay, we left this 3x dy. So how to solve this one? Okay, so we have to go back. We have to go back to the, if you remember, we have to convert it either to the x or to the y, okay, to the t, right? So in this case, okay, so this C is represented by a circular shape. If you can see this circular shape, okay, from the xy projection, you see this circular shape. Okay, we could relate it with the equations of the circle. Okay, this is the equation of the circle. So it's your choice whether you want to use this thing, you want to use assumption, and assume that, okay, the x is cos theta and the y is the r sine theta, or you want to change it to x or you want to change it to y. So okay. No problem. Okay. So this one, I want to try you to switch it to the d theta. Okay, d theta. So I put my r equals to 2 because it's a fixed value, right? It's a 2. 2, okay, cos theta, okay, and then y will be 2 sine theta. So now I want to convert my integral into theta, okay, into theta, because the r could be replaced, but the theta could not be replaced, okay. So the dy d theta, okay, will be 2 cos theta, okay. So now I replace it in my integral. 3x, x is equals to 2 cos theta, okay. dy is equals to 2 cos theta and d theta. This d theta is from here. You multiply it, you can get d theta. Okay, so you get 12 cos square theta d theta. Okay, meaning that you need to find what is the interval of your d theta. Okay, so this is a circle. Okay, so the d theta, okay, will be from 0 to 2 pi. Okay, 0 to 2 pi. Okay, 0 to 2 pi. 0 to 2 pi. So you can press calculator to get the answer. Okay, you can get your answer equals to 12 pi. Okay, so this is the left hand side. Left hand side answer. Left hand side answer. We go to the right hand side. Okay, right hand side is to solve this line integral of vector field using the Stokes theorem. Okay, we go to the right hand side. So the right hand side is about the Stokes theorem. This one. Okay, so this is the formula. So the first thing that you must find out is the curl, curl of the vector f. Let's find out curl of the vector f. Okay, so you put your f here. Okay, so for the first one, yeah, let's hide this thing. So we have 5 minus 0. Right. So this is your I component. Negative. Okay, negative the j component. For the j, you hide this thing. You hide this second column. So it will be 0 minus 2. Okay. And for the last one, you hide the third column. 3 minus 0. Okay. So you get 5. You get 5, 2, and 3. This is vector. It's not coordinate. Vector. Vector. This is vector. So next one. Okay. We go for this. So question mentioned it is outward. Okay, outward. Outward. So what is the equation for outward? Equation for outward is this one. Okay, so this is the equation for the outward. Now let's find out what is the F. What is the F here? So the F is the surface, okay, surface of the paraboloid, right? It's the surface of the paraboloid. So F is equals to Z equals to 4 minus x squared minus y squared. Okay, so the Fx will be negative 2x. Fy will be negative 2y. Okay, so you could replace them. To get your n, you need normal vector equals to negative, negative, positive, right? So you have a 2x, okay, 2y, and 1. Okay, so we get the n. Now, combine with the dx and combine with the interval. So the f is what? The f is 5, 2, 3, dot product, okay, with this 2x, 2y, and 1. Okay, I cancel it directly. So I will put the dA here. I cancel it directly. So let's do it. Simplify it. It will be 10. Okay, so no more this thing because it will be scalar. 10x plus 4y plus 3 dA. Okay, so A stands for the area. So you have to view this paraboloid from the XY projections. Okay, so view paraboloid from XY projection. Okay, so in the XY projection, you will see the circle lah. Okay, so the dA, you will use the polar coordinate. Be easier. Okay, since you want to use the polar coordinate, your interval will be dr and d theta interval. Okay, so dr will be from 0 to, no, right here. dr will be from 0 to 2, okay, and the theta is 0 to 2 pi. Then x. So x will be replaced as r cos theta because you convert into the polar coordinate plus 4, this one r sine theta and plus 3. Okay, plus 3. Yeah, plus 3. So continues to simplify it. So I will take 10 r squared cos theta plus 4 r squared sine theta plus 3r, okay, dr d theta. Okay, so you can use a calculator to do it. But you cannot combine all because it has the cos theta, so you have to press it separately. Okay, so this one you will take out the tan and also the cos theta. You just press the r square, then you get 8/3. This one also, you take out the 4, you take out the sine theta, you just press the r square, same thing, you get 8/3. Okay, you get 8/3. And the last one, you can break 3 out. 2, 0. So you get 6. Okay, last one. Okay, so you can press all together. Okay. Okay, you can get your answer equals to 12 pi. Okay, so this is the right hand side answer. Right hand side. Right hand side of the Stokes theorem. Okay, so when you have found that the left hand side and right hand side are the same, okay, you could say that can write it is proven, okay, or verified that the Stokes theorem can be used to solve the line integral of vector field. Okay, right, so this is about the Stokes theorem. So tomorrow we'll be trying more exercise regarding the surface integral, Stokes theorem, and also divergence theorems. Okay, any questions before I refresh what we have learned today? So basically today we have covered 3 sections. Okay, so the first one is about surface integrals of the vector field. Okay, so the surface integrals of the vector field is used to find the flux, okay, coming out from a surface, okay, from a surface. And the equations is this one. So this is the equations. Okay, so what you need to do is you need to know what is your F, usually will be given, and is whether it is upward or downward. Okay, so upward and downward there will have a different equations. You must be clear. Usually the question will inform you, so you will use different equation for the upward and also the downward. Okay, so next is just to replace them into your surface integral equations, and the dx is something that you can cancel it with the unit normal vectors. Okay, so you can cancel this thing, right? And then perform the integration as usual, and of course you have to define the interval first. Okay, so this is about the surface integral. Then we move on to the Gauss theorem. Okay, Gauss theorem is like a simplifications for the surface integral. Okay, to find the flux coming out from a solid. Okay, so this is especially useful if you have a solid that has many surfaces, because you just need to perform the calculation once. Okay, if you're using the surface integral of the vector field, you might need to perform the double surface integral for several times. Okay, so this is to find out the divergence and then define the range for the dV of that solid. Okay, it's very simple. And last one, we have the we have the Stokes theorem. Okay, so Stokes theorem is used to simplify, okay, the line integral, okay, or convert the line integral into the surface integral. Okay, and of course you have to find a term one by one and then perform the integrations. Okay, perform the integrations in order to get what you want. Right? Okay, so maybe have a look at the notes here first. Then tomorrow we will continue with the exercise. Okay, any questions?
I madam.
Yeah.
Tomorrow we class face to face or online again? Face to
Face
face.
to face kan? Sebab
Hmm.
I will be face to face, right? Or you want to be online?
Face to face.
Face to face
Majority.
Yeah, because I actually follow the vote in the WhatsApp group. Okay, so, because your friend is asking agree whether we agree the class will be online or face to face. So majority is voting online, right? Do you agree? Yeah, so agree that it will be online. That's why we conduct the lecture online. Yeah,
Okay,
that's
so
the reason.
tomorrow.
Yeah, it will be online because
Oh.
31st to 1 of January 24, right? So it means lecture and also tutorial.
Yes, correct.
Yeah, so will be online.
Okay,
Mm.
okay, Miss. Okay, madam. Thank you.
I'm sorry that I cannot perform it online and also face to face at the same time because once I share the screen to the Google Meet, I cannot display the screen in the class anymore, the projector. So it will be very difficult for me to handle. That's why we can only choose either online or face to face. Never mind. Next week, I mean, it's the last week, right? We will try a final examination questions from the previous semesters. So at that time, maybe you all can ask questions lah. Okay, we will ask questions. Right? Any more questions? Okay, if no questions, tomorrow beside doing the tutorial, right, we will also have the group presentations. So which group haven't presented yet? Let me see. So we will have group 13, all right, to present tomorrow. So this one will be group 12 also. 1, 2, group 7, group 6. Think you know who you are, okay? So we will present this thing during the tutorial sections. Okay? Right. So before I end this thing, I would like you to record the attendance. Give me a moment. Let me unshare first. Stop sharing. Because I want to share the things here. I want you to record the attendance. So I need to scan this code for the attendance. For all the sections, huh? 1, 2.
Thank you, madam.
Okay, if you have record attendance, you can leave this meeting. Thank you.
Thank you.